Good morning, everyone. Is it okay? Okay. Maybe we can start this plenary talk. ¿No funciona?
Oh, you have to switch it on.
Yeah. Closer, maybe.
That's better.
Yes, like this. Okay. So maybe we can start our plenary talk for today. Yes? Is it okay? So, good morning, everyone. It's a pleasure for me to introduce Dr. M. Hart. ¿No? ¿No se escucha? Yes? Okay. Dr. Hart is actually working in the field of meta-heuristics optimization for over 20 years. She's active in meta-heuristics and operations research community in the United Kingdom. She's a member of the United Kingdom Operations Research Society panel. She's a member of the Scottish Government panel that advises on development of artificial intelligence strategy for Scotland in the 2020. She's an editor-in-chief of the Journal of Revolutionary Computation at the MIT Press. And just to mention one of her awards, she is honored to be elected as a Fellow of the Royal Society in Edinburgh in 2022. So she's one of the Euro Distinguished Lecturer, so it's a pleasure for us to have her here and keep on learning. So thank you.
Muchas gracias por invitarme por la oportunidad de visitar tu hermosa ciudad. Me siento honrada de estar aquí. And now in English. Okay, so I have had a very interesting 2 days listening to all the different applications that people are working on in operations research, and particularly for me, seeing the different range of algorithms and methodologies that people are using to solve problems. But what I want to talk about today is not just designing algorithms, but instead designing a machine, a software system that can automatically and continuously design and adapt algorithms all by itself, so that as the problems that you're trying to solve are always changing, the machine itself is always adapting to always try and produce the best possible answer for these problems. And this is important for 2 reasons. It would enable, if we could design such a machine, it would enable the machine to learn from experience and improve its performance as it solves more and more problems. But it might also enable the machine to deal with completely new problems or new, very difficult instances of problems that the machine had never seen before. So this means that rather than it's important because rather than just designing an algorithm and the algorithm works well at the time you designed it on the problems that you currently have, in the future, the different problems that your algorithm might face might be very different. And this means in the best case, your solver might still work, but it might not produce very good solutions. But in the worst case, your solver might not produce an answer at all. So I want to think about using artificial intelligence to design this continual machine that's capable of continuously adapting its own software to produce good solutions to problems. So in case you're thinking this will do all of us out of a job, I don't think we're there yet, but I'd like to show you some of the building blocks and some of the things that are going on in different communities, in optimization and in machine learning, that are making the steps towards being able to create such a system. So I've seen many different methodologies and algorithms presented over the last couple of days. And as a community, we already have very good tools for solving problems. For example, Google AI's OR toolbox provides a really comprehensive range of algorithms. If you prefer to use meta-heuristic solvers, then this Nevergrad library from Meta, that used to be Facebook, provides a whole range of gradient-free optimization tools. And of course, we have access to many exact solvers as well. But these solvers have to operate in a very turbulent world. So Anna yesterday already talked about some of the problems that COVID-19 brought up in terms of operations research. So it has a huge effect on supply chains, on logistics problems, on scheduling with people, and Anna talked a little bit yesterday about the difficulties of hospital staff having to move thousands of miles from one hospital to another. So the problems that we were trying to solve very suddenly got very difficult and were not like problems that we'd seen before. We're seeing very similar situation arising because of the Ukrainian war, again with its knock-on effects on supply chains and logistics, but also on energy distributions, which is again changing the way we need to think about optimization. Climate change is also bringing a lot of problems for an optimization community. As it gathers pace and we're experiencing more flooding, more natural disasters, then perhaps the types of logistics problems that we have to solve are also going to change. How do we get, for example, help or supplies to regions that are completely flooded where we can't use the roads anymore? And I think many of us, the UK included, are living in very kind of turbulent times in terms of our economies and our politics, where inflation is rising very quickly, the political state systems are quite unstable. And again, this all has an impact on the types of problems that we're trying to solve. And it means that our optimization systems need to try and keep up with this rapidly changing data in the world that we live in. So I want to talk about optimization in response to a kind of stream of instances. So the kind of domains that I'm thinking about is perhaps in logistics, in supermarket deliveries, for example, where every minute, every second, every hour, people are making orders and a scheduler has to organize deliveries. And you have a constant stream of these deliveries that are arriving every day, every week, every month, perhaps at different frequencies. You also get a similar kind of problem in packing type problems. So here we have some kind of online packing system where our items are arriving on a conveyor belt continuously. They might be changing in shape or size, and your system has to decide how to optimally pack these items. But again, you have this continual stream of instances. So these are the kind of systems that I want to suggest that an optimization should be able to learn from the amount of data that it's seeing from the system and adapt itself to better able to solve these problems by making use of the vast amount of data that it's seeing over time. So I'm going to talk about this in the context of meta-heuristic optimization, partly because it's mainly my background, but also because meta-heuristics have a number of nice properties if you're trying to think about continuously adapting a system. So from a practical perspective, they tend to produce very quick solutions that are good enough, and that's often useful in a practical purpose. They're also good at solving multi-objective problems, which again is realistic if we're trying to solve real problems. They're also generalizable, and if we're trying to think about a machine that can learn, then being able to generalize across instances and even across domains is also a really important thing. And they're also tunable, and this relates to the ability for the system to be able to learn by, for example, adapting its own parameters. So I just want to start off by describing what I think are the kind of 4 key things that I think a system ought to be able to learn, why it should be able to learn them, and the kind of things that it should learn. And then for the rest of the talk, I'm going to talk about some of my own group's work and some of my colleagues' work, and show you some of the building blocks that might be used to put together to create this kind of system that I envision that is really capable of, by itself, completely adapting autonomously to new problems. So lots of these, so you'll see as we go through, I'm borrowing lots of ideas from different communities. The machine learning community in particular seems to be much further ahead than the optimization community in really thinking about algorithms and systems that can continuously learn. And I'll show you where I think that we can borrow some ideas from their work, although in a very different context, as well as from optimization itself. Okay, so my number 1 reason is that optimizers should learn from experience. So as people, we all learn by doing things, and the more we do things, the better we get at doing those things. So particularly if you're learning to play sport or a musical instrument, the more you practice, the more you get better at doing that thing. And you get better because you learn to spot patterns that you can reuse from one situation to the next, and you learn kind of tricks that you can redeploy in different situations. And I think that optimizers should also be able to do this. If you have a solver that is solving hundreds of logistics problems every single day, then that solver is seeing a huge amount of data that it could learn from. It's a kind of knowledge base of data that the system ought to be able to extract useful information from that knowledge base and reuse that information in a different situation. So for example, if a new instance comes along, it might be possible to completely reuse a solution from a previous instance, or at least it might be possible to partially use a solution that you've seen in another instance. So essentially, every time you solve a problem, you're creating some data. And we ought to be able to mine that data to find useful information that we can feed to our solvers so that solvers themselves can get better the more they experience solving problems. So a second really important thing is that these solvers ought to be able to react, in fact, predict and then react to changes in the environment. So if the data, the instances they're trying to solve is changing, then the solver themselves must also think about changing. And data can change in two different ways. So one is drift, which is like a gradual change over like a long period of time. And then the other is the very kind of sudden change that we saw, for example, in COVID. So this graph, it's really a proxy for how much data might change, but it's the number of Google searches over a 10-year period from 2010 to 2020 for food deliveries. So this is kind of like a proxy for how like online delivery scheduling systems, how the data that they're dealing with must have changed over the last 10 years. So you can see like between 2010 and then the early part of 2020, we get this very gradual drift where there's more and more orders coming in, and of course that means that the problems you're trying to solve are likely to be more complex. And then all of a sudden, we all know what happened in 2020, you get this huge rise when the lockdown started around the world. And so again, for an optimization system, the data now that it suddenly has to deal with must be very different than what had been happening over the previous years. So I know this is a little bit hard to read, but I think this illustrates quite nicely how fast data can change. So this is a graph that just shows 2 weeks in 2020, the week in the UK before the lockdown, and then the week of the lockdown itself. And it shows the kind of things that people were ordering from shops compared to the same week in 2019. So it's the percentage difference in the order. So what you see in like the week before the lockdown, there's this like more than 100% rise in frozen meat, in baby milk, and in savoury home cooking that people were ordering compared to to the same time the year before. Then just a week later, when we suddenly were all put into lockdown in the UK, everything completely changed. The things that people were buying changed. So now alcohol suddenly goes near to the top of the list, and people want sweet home cooking as well as savoury home cooking. So I don't really have an explanation for why people want to buy these things, but I think it just illustrates how the data can change so fast and why our solvers might also need to change. So another thing that I think that optimization systems should be able to do is learn across domains. So this is really typical in the machine learning communities. So for example, people that work on natural language models, so you get these very good neural networks now that can translate languages or predict the next word in a stream. And they're often trained with multiple languages because by learning cross-language, you can actually get a better system. You see it a lot also in the computer vision area where people are recognizing images in photographs. And let's say you want to recognize images of dogs. It turns out to be helpful to also show your network images of other related animals. And the system does some sort of cross-domain learning across these domains, which actually helps it solve the problem that you want to solve better. So again, I think there's some opportunity to use this kind of thing in the context of optimization. So if you take something like a supply chain, where you have multiple, essentially permutation-based combinatorial optimization problems. So you might have scheduling in a factory, you might have packing in a warehouse, you might have routing to deliver those items, but they're all examples of similar but related problems that have this feature where they're essentially permutations and combinatoric. So there seems to me here, again, some opportunity for a machine that's solving problems to learn cross-domain, across these different types of problem in order to better solve the thing that you want to do. And I'll show you some examples of this later on. So finally, it's also important that the machine doesn't just get better at what it's trying to do all of the time, but also it's able to handle completely unexpected tasks. So for example, due to climate change, if suddenly the roads are really flooded, we can't do deliveries anymore, well, maybe we need to switch to drone deliveries, okay? But this is a completely different problem if you're trying to schedule drones, if you're trying to schedule or route transport trucks along roads. So it would be nice if our optimizers didn't just break when they were faced with a completely new task, but they could actually figure out how to handle this completely new task by themselves, given an objective function and some data to do that. Okay, so these are my kind of 4 things that I think a machine should be capable of learning. So the machine learning community, again, to go back to them, is ahead of the game, I think, compared to the optimization community here. So back in 2013, there was this really seminal paper from Silver who proposed what I really said at the start, that we shouldn't just be designing algorithms, but what we should be designing machines that are capable of continuously learning over the whole period of time that you want to deploy that machine. And in fact, in the US a few years ago, DARPA, I'm sorry if you can't see the bottom of these slides, DARPA funded a big research program on what they called lifelong learning machines, L2M. And their idea is that rather than having a system where you basically teach the system what to do, you train the parameters of your optimizer, and then you put the system to use, and then it just keeps operating in exactly the way that you told it to do. What they were envisaging is rather than that, we should have a system that, as it's being used, it gets better and better at performing that task because it's seeing more and more examples of the kind of things that it has to do. And in fact, not only should it improve with time, it should also be able to deal with surprise. So if your system is suddenly faced with something that it can't handle, if your system is not capable of adapting, then it breaks. And you don't get any solution at all, and that's what you see in the orange line there. But what they're envisaging is that you should try and design machines that, of course, if something drastic happens, the machine might not work for a small amount of time, but then it should relearn how to solve the task that you're asking it to do. So it really has these 2 capabilities, the ability to learn from experience and the ability to deal with completely unknown situations. Okay, so what I want to do now is show you some of what I think are the building blocks of being able to design such a system. And then we'll go through the building blocks and I'll show you some examples of small pieces of work where people have tried to tackle some of the challenges in this area. Now, there's very many challenges, and I don't know of any work where anybody has built a whole system that can do all of the things that I want to show you today, but I think we're making progress in the building blocks in a way that eventually we might be able to build such a system. So I know this is a somewhat complicated looking diagram, but some of the things that I think we need to be able to do. So if you basically we have a stream of instances and we want to get a stream of solutions out the other side. So there's a number of pieces in this jigsaw. The system probably needs to be able to do some kind of feature extraction on instances to understand, for example, is this instance like a previous instance? Because that's useful information in deciding how to go about solving it. It's quite likely to involve a portfolio of solvers because there'll be no one optimizer that will work across all problems. So it seems likely that we need a portfolio of different solvers. And if you have a portfolio of different solvers, then you need some kind of algorithm selection mechanism that's capable of saying, well, for this instance, we need to use that algorithm, and for this instance, we need to use a different algorithm. I'll talk about this map in more detail later, but it's a way of kind of visualizing what do our instances look like? Where in this space of possible instances are we currently seeing instances from a domain? Where might we see instances in the future? And then the part along the bottom is really about this idea of reacting to change. It's about the machine being able to speculate about where the instances it might see in the future might be. So it knows what it sees today. It maybe can sort of predict with relative accuracy what it might see next week. But we want to be able to say, what might the instances look like in a year's time? And if you want to predict where those instances might be and you want to find a good solver for doing it, then you need to, first of all, predict where they should be. Then you're going to need to generate some synthetic examples of those instances, and then figure out what kind of solver do you need for these new instances that we think we might see in the future. And perhaps you don't even have an appropriate solver, and the system might even need to design its own solver. So there's many pieces here, each of which probably could have had completely its own talk. But I'll try and go through some of these pieces just at a high level to kind of show you the kind of things that people are doing to make some progress in this area. So there's lots of opportunities for learning in this diagram. So the first one is really this data-driven improvement. If you're seeing many, many instances, if you're solving hundreds or thousands of instances a day, then you ought to be able to learn something from that mountain of data that you're collecting that helps you solve instances more quickly or better in the future. One of the things that you probably need to do is rather than just adapting the algorithm selectors, is also adapt your solvers. And the simplest way you can adapt a solver is by tuning its hyperparameters. So it's very likely to involve some kind of learning that involves online dynamic tuning of your solver to the stream of instances as the stream changes. And then we're also interested in this idea of, first of all, detecting drift in the data and surprises in the data, and then being proactive about how you might react to that. So you don't want to just wait till something happens and the machine doesn't work. You want to try and predict what might happen in the future, and then be prepared for when that actually happens. So many opportunities here for applying ideas from learning within this context of optimization. Yeah, and then finally, the last piece is just to be able to generate completely new solvers if you don't have any that are appropriate for these new instances. Okay, so let's talk about these one by one, and I'll show you some of the examples of things that people have been doing. So this first thing is this idea about how can you learn from experience, how can you learn from all of the instances you solve in the past to what you might do when the next one comes along. So we're really working in this part of the space where we're looking at this data-driven improvement by just trying to extract useful information from the data that we're collecting by solving previous problems. So a lot of this goes back to this algorithm selection. Of course, everybody knows from 1976 by Rice. And really what we're looking at here is this part here where we're trying to do this mapping from algorithms to performance and figure out for this instance which is the best algorithm from my portfolio that I should use to solve it. And you might have criteria for best there. It might be based on time. It might be based on actual objective function value. So a typical way to do this is to use some kind of machine learning method, and you build a model, and typically what people do is they extract some features from their data. So you have some domain-specific features, and then you train some kind of machine learning model. It can be a neural network, it can be a tree-based classifier, it can be anything that you like, to basically learn a mapping between the features of an instance and then the solver that is best for predicting that instance. So if we switch to thinking about this stream now, and then this kind of continual stream of data that we're seeing, and we want the machine to basically update itself as it sees new data, then one of the kind of obvious things and seemingly simple things that you can do is essentially periodically retrain your model as you get more and more data. And that kind of makes sense that as you train your model, it does okay, and then maybe at the end of every month, because you've seen many more instances, you retrain the model. So that kind of makes sense, although there's some quite recent work from the neural network community that suggests it's a little bit more difficult than you might have thought. So so there's two ways that you could think about doing this training. You have some existing data that you've trained your model with, then you've got this new data that you've collected. And so what you can do, what you call a warm start, is basically you retrain your model, but starting from the model that you currently had. But instead, you just show it now all of the new data. Okay? So that seems to make sense because you've already learned a model that did okay. The opposite way to do it is what we call a cold start, is you basically just throw away your model and you completely retrain from scratch using all of the data that you've got. So there's some interesting things that happen here. So actually the blue line here is the warm start and the yellow line is the random start. And actually you see what is quite surprising, that if you do this warm start of starting training from your previous model, you actually get a worse performance than you do by throwing away everything and starting from scratch. But the flip side of that is if you look at the time it takes to train your model, then retraining from the original model is very fast. Retraining from scratch with the new model and all of the new data really increases, the time increases very rapidly as you have more and more data. So there's a kind of trade-off here between whether you're interested in how often you retrain and whether you're interested in accuracy or whether you want very fast adaptation, in which case you might be more interested in the method that learns faster than that. So there's still some work and some challenges to do here in this what seems like a fairly straightforward thing of just kind of retraining your models as your data changes. And there's some other problems with this feature-based algorithm selection, I think, as well. So partly trying to extract features from your data typically relies on some kind of domain expert that understands very well what the features of the domain are. And often these features can be very computationally costly to extract. So typically in things like routing, a traveling salesman problem, a lot of people use very complex features that are based on graphs and kind of calculating the sort of clustering of the cities and other graph metrics that tell you something about the layout of the problem. But a lot of these are really expensive to compute, particularly if you're talking about like hundreds or thousands of cities. So they're not always useful. And another thing that I think is often not talked about is there's not necessarily a correlation between what we see as humans as features and what an algorithm sees as features. So we can have two examples of instances that might be very close in the feature space, but when you look at the performance of one algorithm on those two instances, you can get very, very different performance. Okay? So there's not always this obvious mapping between features and algorithms. So partly in an attempt to address this is work from one of my students who decided, okay, let's stop trying to look at features altogether, and let's try and train the model using just raw data. So this is a bin packing problem where you've just got the size of the items that you need to pack. And he takes inspiration here actually again from a natural language model. So this LSTM is a kind of neural network that's normally used in language applications where you feed in a sequence of words in a sentence and it predicts the next word in the sentence. So what he feeds in here is just the size of the items and the model predicts the best solver with really good results without having to extract any features at all from the data. I've also tried to look at this feature-free methods of doing algorithm selection. So I don't know how clear that is, but this is again in traveling salesman. So here, they just represent the problem as an image. So each dot on the graph is just the location of a city. And what you feed to the model now is the picture of the map. So you don't have to calculate any metrics about how far cities are. You just feed an image that shows the locations of the cities. And then you use a convolutional neural network, which is a special neural network for dealing with images that basically can take in the images and learn to predict the best solver based just on the images. So this is really good, particularly if you have a new domain where you don't know what the features are, so you don't know how to extract the features in order to do algorithm selection. If you have a way of just feeding the raw data in, either as a sequence or as a picture like this, then you're able to try and teach the model without having to know anything about the features of the problem. And that would seem to be important if we're going to make progress in this area. Okay, so just to talk a little bit more about tuning in this respect, then if your data is changing, how can we automatically tune our solvers to do better? Okay, so this is an example of a piece of software that I've heard people talking about over the last few days, iRace. It's an automated algorithm tuner that tunes the hyperparameters of algorithms. And basically what it does is it searches over the space of the parameters of the algorithm. For each candidate configuration of those parameters, it evaluates it on a whole bunch of instances that you want to solve, and it uses that information to update the search process to find a good set of parameters. And this really works well. I don't know if you can see that if you're sitting lower down, but you can see on this graph, hopefully you can see in the graph at the bottom, is an untuned version of a solver on the set of instances and the tuned version. And you really see that you can make massive gains by tuning your solvers properly. So tuning in response to changing data is really important. And just to kind of emphasize that even further, this is a really nice paper from Meinhof Selman and his group, where they're working in constraint-based SAT solving. And they had this paper a few years ago where they showed that you could win a SAT competition not by writing good algorithms, but by taking some of the algorithms from the competition 2 years previously and just tuning them properly. Okay? So without having to actually waste effort on trying to design new algorithms, by actually just tuning existing old algorithms, they get a better result. And they say in the paper, essentially, they're making up for 2 years of development time in what is actually a very fast developing community. Okay, so that's tuning to do essentially small changes in response to a stream of data that's probably not changing too much. So I want to spend a little bit of time now talking about drift and surprise. And there's two things here. First of all, we need to recognize the drift or the surprise, and then we need to do something about it. Okay, so we're now working in this part of the space where we're trying to figure out what is going on with the stream of instances and if it's changing over time. So again, the machine learning community do a lot of work in this sense. So for example, they do a lot of work with like multivariate problems where you have variables that are changing over time. You have some sort of reference period where you monitor what's happening. And then in your analysis period, you want to figure out, are these variables changing sufficiently that as a whole, the instance has changed in some way, okay? But this is quite difficult to utilize, because if you have an instance that you're trying to solve that has many, many variables, even though you can track the change in individual variables, it's hard to know how those variables are interacting with each other and whether the total amount of change means that actually your instance is sufficiently different than a previous instance. So you need some way of kind of looking at the big picture and saying, even though if we track every single variable in the problem and how it's changing over time, do we kind of figure out whether actually we are now dealing with a different kind of instance? So one thing that people do is train a model. So you take your data that what you consider to be normal, what is a selection of instances that we're currently solving. And then you learn this model, which is a low-dimensional, typically two-dimensional projection of that data, okay? And then, so you compress your data into a low-dimensional projection. And let me show you. And then you uncompress it again. So this kind of sounds a bit odd, but the idea is that if you learn a model on your normal data, you learn to compress it and then you uncompress it, the uncompressed instance should be the same as the instance that you compressed, okay? So if you've trained this model to do well at compressing an instance and then uncompressing it back to itself again, then you have a model that detects your data. So then in the future, if you have a new instance, and I'm just showing this with an image instance, you compress that and then you uncompress it, and then you get some image that doesn't look like your original data, we can measure the amount of error between what came out and what we put in, and we can use that as a measure of how different our instance was to the previous instance. So we can measure this reconstruction error, and it gives us directly, using this model that was trained on the normal data, some measure of how the instance as a whole has changed without having to examine all the individual variables. Okay. So for example, here's an example of this working. So the blue section at the start is the data the model was trained on. And then the purple section is when the data started to change. And what we're just looking at is the reconstruction error of the instances. So over time, in the immediate period following the training, there wasn't much change. But then suddenly we start to get this big rise in reconstruction error. And we can figure by setting some threshold, now we know that we've got sufficient change in our instance data that we need to make a change in our solvers. So a different way of thinking about exactly the same thing comes more from my own community, the meta-heuristic optimization community. And so this is a methodology that was introduced in Australia by Kate Smith-Miles and her group that they call instant space analysis. So this has some really nice properties. So the idea is that you can take a big set of instances from a domain, you can calculate some features, and then you can, using those features, you can project those features again into a low-dimensional, in fact, two-dimensional space where you can visualize things. So what you see here, the instances from timetabling domain. These are instances from different benchmarks. Some are from a competition, some are from a random generator, some are taken from the real world. And when we project them into this space, that you can see that the instances from the different benchmarks lie in different regions of the space. So it suggests that there's something different about the instances from one benchmark to the other. It also enables you to calculate a kind of bounding box, which is the space in which we think the instances might lie. And this tells us another useful thing, because in the areas where there's nothing, then we know we don't have any representative instances in that parts of the space, even though those instances might exist. So if we suddenly have an instance that arrives here, then we don't know which solver is going to be good for that instance. So it's a very nice way of trying to understand a huge set of instances and how they relate to each other. And we can do multiple things here. So this is the same diagram of the projection into the space, but now it's colored depending on how two different solvers behave. So we have some threshold that we say the performance from the solver is either good or bad. Blue is the good, yellow is the bad. And so what we can see here from this solver on the left is that it's not good in this region at the top, but it's pretty good in this region down here. Whereas if we look at the other solver, we see something different. We see that actually it's not good on those yellow instances that lie to the left of the diagram, where it's much better on the instances that lie to the right. So now we can start to understand where, not only how different our data is, our instances are from each other, but we can also start to see where algorithms work well or badly. And again, you can just recolor the same diagram. So now this is just for the same solver, but it's colored according to performance, where blue is good performance and yellow is the worst performance. So you can see within the solver space where the solver is very good, where it has kind of average performance, and where it has weaker performance. So it lets you understand the strengths and the weaknesses of your set of solvers in relation to a very large set of data. And then if you can do that, you can start to basically, if you've got a portfolio of algorithms, you can start to see the sort of footprints of these algorithms. So where in the space does one solver work, where in the space does another solver work, and the bits in the middle that are not colored basically means you can use either of your solvers. So these diagrams are really useful, if it turns out, if you're trying to think about drift and surprise in your data. Because we can use them to say, okay, if we've got some new instances, where do those new instances lie? And if we can see they lie outside what we know to be the data that we've been solving in the past, then we can see already there's some drift because they're starting to lie outside of our set of original instances. And then also, if they lie really far away, then there's more like the surprise when they're really very different from the instances that we've currently been looking at. So we can use these kind of diagrams to kind of project as our stream of instances arriving, we can project into the space and then see where they lie in relation to what we know and what we've used to train our portfolio on, and then decide, okay, now we can at least recognize that we've got something different going on here, and we need to figure out what kind of solver to use. Okay, so now this allows you to start to at least recognize that something has happened. So what should you do if you think this has happened? Well, one thing that you could do is just trigger a tuning event to change your solvers. Perhaps just change their hyperparameters. It might trigger retraining of the model that maps your solver, the features to the solvers. So you might need some kind of threshold here to distinguish between drift and surprise. So if you can see in the instance space how far away your new instances are, you might decide to do one of the first two things if they're very close. But if they're really far away, the data's really like things that you've never seen in the past, then you might need to do something a little bit more reactive. So one thing that you can do here is like what happens if you find out that you've got some instances that are nothing like anything that you've seen before and none of your solvers work in this part of the space. So we can try and deal with this by trying to do some sort of online automated algorithm generation. So here we're really working in this part of the diagram where we've kind of recognized that now we think in the future there's going to be instances down in that bottom corner here. What are we going to do about that? So if we think there are going to be instances there, we don't have any examples of them, we'll have to generate some instances, some examples of synthetic instances that we can use to basically then train some solvers. We might train our existing solvers, but we might find that we don't have anything that works and we need to find a new solver altogether. So one thing you can do is have this an approach to this that actually is relatively old now, is to have this dynamic algorithm portfolio. So if your instances are changing, you don't need to have a static portfolio of solvers, that your portfolio itself might adapt over time. So that can adapt in two ways. Either the composition of the portfolio changes, so you can add new algorithms to the portfolio, or you might adapt the algorithms themselves. So a lot of this work, again, in SAT solving, builds on this idea of basically essentially creating new solvers by combining building blocks from existing solvers. And there's a line of work here in SAT solving that followed that. I just wanted to show you again some work from my group. So this is very loosely inspired by looking at the human immune system. So as people, we're faced with this kind of continual stream of pathogens from the environment that are basically entering your body. And what your body is doing is continuously generating immune cells to try and fight those pathogens. So this is very loosely based on this idea that you have this stream of problems coming into the system, that's the square heuristics, that's the circles. And then you have this heuristic generator at the bottom that is continuously generating heuristics to solve these things. And it just throws the heuristics into the system, and you essentially have a competition between the problems that are coming in and the heuristics that are competing to solve those problems. So it's a kind of opportunistic generation of solvers. Each heuristic competes for instances. Heuristics that turn out not to be good just disappear. Heuristics that turn out to be good stick around. But of course, this can change over time, and if your instances change over time, then sends the current heuristics that are in the system, some will disappear, and some new ones will come in. And we showed this again in bin packing, that this could really react to quite high frequency change and also low frequency change in data. And also it's capable of maintaining some kind of memory, so that if a heuristic was useful in the past, you can keep some memory of it so that it's also useful in the future. Okay. So what do I mean by heuristic generation? So this is just really simple in bin packing. You have a number of off-the-shelf heuristics that are constructive heuristics that add one item at a time to the bin. So you can essentially generate a new heuristic as a sequence of existing heuristics. Another way to do it is actually to modify the heuristics themselves. So this is using a kind of decision tree that takes in some features, and it's basically each new tree is a new heuristic that tells you how to pack the next item. So you can in fact use both methods to do this continual generation of new algorithms into your system. Okay, so I think it's really important to be able to be more proactive about these things. So I've talked about recognizing surprise. But rather than just recognizing when it happens, it would be much more useful to be proactive, to predict when and how that surprise is going to happen, and then do something about it before it actually happens. Okay. So here again, we're talking about this kind of space here. So we want to say, what are my instances going to look like in the future? Can I make some new instances that look like what I think I'm going to see, and then figure out how I'm going to solve them? Okay. So again, machine learning has some things to say about this. So as vector autoregression is a way of doing multivariate time series forecasting. Again, it's a way of saying I've got multiple variables that are all changing, and it's learning a model that treats them essentially as a time series and figures out for each of the different variables, what are we going to see in the future. But it's the same thing as I said before. It's quite hard to do this when you've got very many variables and they're all have either dependencies or not dependencies between them. So another way to do this is to go back to these instance-based models and essentially have your computer, your machine, dream about what it's going to see in the future. Okay, so it knows it sees these instances now, but what it can do is speculate, okay, well, I think, I see this now, I see this now. Maybe it speculates that in the future, you can look at the kind of direction of travel of where your instances are going, and you can kind of guess where they might be in 1 week or 1 month or 1 year's time. So we might guess that they're going to be in that region. So then the next thing that we need to be able to do is generate some instances in that region to test. Okay. So just looking at a slightly different one. So this is just another, is from I think this is from graph coloring. So these are the set of instances in the colors that we currently have. What if we predict that the instances in the future are going to be down there where those circles are in the corner? So one thing that you can do here is try and generate the instances that lie in this region. So one way to do this is to kind of identify the space in this 2D map where you think you want to be, and then use something, and in my case we use an evolutionary algorithm, to evolve new instances, so not solutions, just the instances themselves that lie in that region of the space. So we can basically give our evolutionary algorithm the objective of saying we want instances that look like that, and you can run the algorithm and you can generate many instances in that region of the space. So here's just something that's been done actually to fill up the whole space. So the red and the green are the instances that came from benchmarks or real-world examples. You can see with the bounding box, that leaves really a large amount of the space empty. So we can really improve our ability to do optimization if we try and fill up this space with instances. So this is using an evolutionary algorithm, and it's just been asked to fill up the white space. And you can see that it's pretty good at finding new instances that now really cover most of the space within that bounding box. So this gives you a much better representative set if you want to start to learn how to apply your solver in that space. So if you've got new instances, then we need to think about how we're going to solve those new instances. So it might be that an existing solver can be tuned, but you might want to generate a completely new solver. So this is an offline approach. It's again based on iRace that tunes parameters, but here iRace is being used to actually generate new algorithms. So essentially you can represent an algorithm as a kind of grammar, and then you can use some search process to basically use this grammar to search for new descriptions of new algorithms. And then just like using iRace for tuning parameters, you search over the grammar. You have to have a piece of software that turns the grammar into executable code, that you then run the code on the set of instances, and then you just run this system until you get your new solver. So for example, let me just skip through that. Here, so this is learning a new iterated local search algorithm. So you can specify a template of a local search algorithm. It's got a number of steps. Each of those steps can be instantiated in many different ways. You have some kind of grammar that basically represents how a new algorithm should look. And then you can basically use this to learn a new algorithm. This has been used a lot in the evolutionary community in multi-objective optimization. So this, again, is just a template for a multi-objective algorithm. You can instantiate very many of those steps. So the number of possible combinations of different ways you could do this is so large, you can't do it in any kind of methodical way. So you need to use some kind of meta-heuristic search process. But just to show you, so this is the results of the automated design of the algorithm compared to the state of the art in multi-objective evolutionary algorithms on a set of instances. And you can see it's on 3 different instances. And you can see that every time the evolved algorithm is much better than any of the off-the-shelf approaches. OK, so I'm going to finish up now by just talking about the last piece of the jigsaw here, which is about this idea of transfer learning. So this is, as I said at the start, this is very common in the machine learning community. And I think as an optimization community, we have something to learn here. So it's really this idea about being able to optimize across multiple domains. So there's multiple things that you can do here. You can either use this transfer learning to either generate new solutions to problems, or you can also use it to do algorithm selection. But the idea is kind of the same in both cases. You have multiple different domains. They're all feeding information into this kind of shared knowledge base. And the idea is that if you're trying to generate solutions to any one of your problems, you can learn from the information in this shared knowledge base. And there might just be some partial piece of information that you learn from one domain that you can reuse in a different domain. It's kind of the same with algorithm selection. Here you're learning a model to do algorithm selection, but you're training the model on multiple domains rather than a single domain. So you might be training it to predict solvers for TSP, solvers for bin packing, solvers for job stop scheduling. And the model is seeing examples of all of these different domains. And by learning across the domains, it's able to do better on any single one of those domains. So we just look at that in a little bit more detail. This is what's generally referred to as MTO, multitask optimization. So this is basically, again, using population-based meta-heuristics. So if you have a population and you have multiple domains, I don't think you can see the colors very well. So one thing you can do is basically have one population, and your population has solutions from all of the domains that you want to solve at once. And then you can basically have kind of cross-transfer of information between solutions from each of the different domains. So when you're searching for solutions, you don't have to just kind of combine information from 2 solutions from the same domain. You can actually combine, which seems a little bit strange, information from different domains. A slightly different way to do it is maintain separate populations with the solutions from each of your 3 domains, but then periodically you stop and you share information across the domains, and then you carry on learning or searching within each of the domains individually, again from another period of time, and then you just repeat. And actually, this works surprisingly well. So this is just some results. It is on 4 domains. So it uses traveling salesman, a linear ordering problem, a quadratic assignment, and job shop scheduling. So the green and the black is when you just learn on the domain in an individual domain. So it's looking at 2 domains at a time. So if you just learn just on TSP, that's the black line, or just on the green one, which is just on the other domain, you get one solution. But if you learn cross-domain and you just look at the solutions for each domain individually, you can see that you get much better solutions when you're learning cross-domain. And actually, it's the same for each of the combinations of pairs. So you do it with the quadratic assignment and the job shop, and again in the final one. And you can see that actually in most of the cases, particularly in the left-hand 2, you get much better solutions if you do this cross-domain learning. So it's very hard to understand what is actually being learned here. It doesn't seem kind of entirely obvious how you can transfer from one thing to the other, but somehow the evolutionary process here is able to kind of find patterns in one domain that it can reuse in a separate domain. So, of course, this is not easy, and this is a new field, particularly in the metaheuristic field, that is kind of really rapidly taken off. There is a number of issues that still need to be solved. So the first one is this kind of negative transfer, and so that's really saying this only makes sense if your domains have something in common. So if you have 2 completely different domains, it might not make sense to do this cross-domain learning, because you actually might get a negative effect from trying to learn cross-domain. So you have to be careful about the domains that you choose to learn across. You have to be careful about the algorithms that you choose to be able to do this. One thing that is actually really important is if you're going to have cross-domain learning, then you need a unified representation of your solutions. So you need to be able to represent your solution for a traveling salesman problem in exactly the same way as your solution to a job shop scheduling problem. So there's a lot of work going on to try and figure out what should these unified representations be. Can we find some way of representing things that allows us to represent multiple things in the same way? And some of this goes back to what I was saying earlier about the feature-free representations. So, for example, using images, for example, might be one way of having a unified representation, because you can represent packing problems actually as an image, or you can represent graph coloring as an image. So using images might be a way to get around this. And then, of course, the question of how do you do the sharing? What do you share? When do you share? How frequently should you choose to share things? An area that really has been looked at a lot in the machine learning community, but I think offers really a lot of opportunity in an optimization domain. Okay, so I'll just finish up by saying where do I think this is all going? So this is what I think systems should be able to do. They essentially used to be able to practice at tasks. If they're solving lots of instances, they're always accumulating data from the tasks. So the key thing is to be able to do the third thing on this list, which is really extract and use this meta-knowledge from the experience of, like, what did the solver do while it was solving it? Why did it create that solution? Can we extract some information from there to understand how better to solve the next problem? I think systems shouldn't just get better at solving the one thing that they're doing. I think it would be incredible if we could create systems that are capable of learning new tasks, or at least recognize when a task is sufficiently different than a previous one, and be able to solve that. So obviously there's a lot of work to do to figure out this thing between efficient and effective knowledge transfer between instances and tasks themselves. And for it to work in practice, it really needs to be scalable. So I think this is a cross-community kind of task. I think there's lots to learn from machine learning. I think there's lots to learn from the optimization community as a whole, whether that's through metaheuristics or any other kind of optimization, and clearly from the operations research community. And I think the more we learn from each other in this respect, that the more progress that we can make in solving some of these problems. Okay, I'll just finish up. I just wanted to show you, this is a picture of my home city today where the temperature is something like -5 degrees. There's been a 40-degree temperature difference between here and Edinburgh and some of the last days. So I'll just leave you with that and say thank you very much.
Okay, we have some time for questions.
Thank you very much for your nice talk. I have a question about this SAT competition. You mentioned that there are finite number of algorithms. There are finite number of algorithms, and you use them in order to create a new one. Is this what? I mean, you said that they're 2-year-old algorithms.
Yeah. So with the 2-year-old algorithms, they weren't essentially creating new ones, they were tuning existing algorithms. So I guess the tuning is in 2 ways. It can be to do with the parameters, depending on what the solver was, or it could also be to do with like the components within the algorithm itself. But but it was mainly to do with the tuning of parameters, and just by tuning those, you can.
Because what I would do from scratch is to run. I receive an instance and I run.
Yeah.
In parallel all the algorithms, and the first one that gives me the answer, I keep this the output. So why this is not? I mean,
because you can. So that's okay. It depends on the portfolio, but you might not. You can get an output for running all of your things in parallel, but you can get a better output possibly if you tune those solvers that you currently have to the instance that you're trying to solve now. So it's really about this ability to do like very fast online dynamic tuning and say, I'll take the solvers in my portfolio, but I'll tune the parameters very, very quickly based on some information that you can extract from the problem to basically make the same solver work better, but by tuning it to the instance that you have. So it's about dynamic tuning, very fast and the things. Yeah.
Thank you.
Thank you very much for your very nice talk. So I was wondering, in the feature that you use this evolutionary algorithm to generate new instances.
Yes.
How likely it is that the actual surprise comes from sort of different features? Because as I understand, you have like a 2D projection from these instances to a very reduced model, and you explore this region. I assume you explore from the instances and then they get projected.
Yes.
But is there a risk of then they getting like trapped into evoluting into the wrong direction that the surprise is actually going to come?
I guess it's possible, and it's also because, so you can sort of predict the direction where you think the things might be going, okay, but it's not necessary that will be a surprise. I mean, maybe it's a surprise because they're in that part of the space rather than this kind of the space, but you don't know that it's a surprise from the algorithm's perspective, and like whether the algorithm will still see it as a surprise. And that's not exactly an answer to your question, but like it's definitely something to consider. I think you're partially right, that because this model has learned something about the projection from the features, and so you have possibly learned not incorrect, but not the right model. Yeah, like a different model will give you a different projection, right? And so, that's a difficult question, is like what the right model to use is that gives you the best 2D projection, and whether actually your model doesn't handle very well completely new instances, that it doesn't project very well into the new. So you could have a new instance that when you use the learned model doesn't project into the right place in the space because it's giving you wrong output. Yeah, there's definitely something that needs some work.
Thank you very much.
Any other question? If not, I have one. There's another. Again, thank you for the talk. And I have one little question. How do you manage the big amount of data? You use, you keep all the information, you select?
Yeah, so the simplest way is to kind of manage a fixed amount. And so like with a sort of first in, first out approach. And so you know, as you get new data, you lose the oldest data. Of course, there's a risk in that in the future you might see something that you've lost from the past. So that's also a challenge here, is to know the right amount of data that you should be keeping and what planning period you should be looking over, that were horizons to figure out the best thing to do. Yeah.
Of course. Well, we would like to thank again.
Thank you.